What's up, everyone? Today we're going to go over longest path in a directed acyclic graph. Now the input is going to be a DAG and the output needs to be an integer, in this case 3, and this represents the longest path in our DAG. Let's go over the basics of graph theory. So a DAG is a graph where we have edges which are directed, so we can go from, let's say, 2 to 3, but we cannot go from 3 to 2. And as it's acyclic, which means that there are no cycles in our given graph. So let's look at how we get the output. The output is going to be the number of edges between any node and the farthest node we can go traversing the paths. So from 5, we can have an answer of 3 because we can go 5, 2, 4, 3. So there's 3 edges. Or we could go 5, 1, 4, 3. So there's 3 edges. Let's see how we can break this down. Alright, so I've taken the previous DAG and I've broken it down into separate components. Now, we don't know which node is going to have the longest path starting from itself in the entire DAG, so we have to essentially check all of them. So I've written it down such that I have a starting node, the different paths that we could have from that starting node, and the result if we were to start from that node. So if we started from node 1, the output would be 2 because we can either go 1 to 3 or we could go 1, 4, and 3. So the result is going to be 2 because this is the longer path. Similarly, for 2, we can go from 2 to 3 or we can go 2, 4, and 3, and the output starting from node 2 is going to be 2. If we were to start at node 3, we can see it has no outgoing edges, so the longest path starting from node 3 is going to be 0. If we were to start at node 4, the longest path starting from node 4 would be 1, simply because all it can do is go to 3. Now this is the interesting part. If we were to start from node 5, we see that there's a lot of ways that we can actually go about it, right? We can either go to 3, or we can go to 3 from 2, so 5, 2, and 3, or we could also go from 5, 1, 3. And there's another node, so we can go to 5, 2, 4, 3, and 5, 1, 4, 3. So let's figure out how we can save our time so we don't have to recalculate everything. We already see that, hey, I'm reusing components that I've already calculated before when it comes to 5, right? Whether that's having to start from 3 or whether that's starting from 1, I'm sure there's a way that we can reuse what we already calculated. And that's essentially what this problem is. It's overlapping subproblems. If we want to calculate the longest path starting from 5, we can first try to see if there are any subproblems that we can store and reuse it to save computation time. So let's look at that in a more finite detail. Alright, so I've just mentioned we are going to be using subproblems, and when we have overlapping subproblems, approach it with a dynamic programming approach. So the question then becomes, which subproblem should I solve first? So we know that if we start from 5, it's going to be complex because there's different paths we can take. What if we start from 4? Sure, it's a shorter path, but it's still not the most basic of units. In our graph, the most basic node we have is 3. We know that 3 has no outgoing edges, so we can guarantee that the longest path through 3 is going to be 0. Now, any node that is pointing to 3, so something like 1 or 2 or 4, can reuse the most basic unit we have from 3. So anytime 1 is going to ask 3, or 2 is going to ask 3, or 4 is going to ask 3, 3 is going to say, alright guys, my value is 0, so I'm going to say 0 plus 1 because the distance between you and me is 1. We have one edge that separates us. So the answer 1 or 4 or 2 is going to get is going to be 0 plus 1. Now that we've seen a specific example, let's look at a more generalization and derive our DAG dependency from that. Now, I've written a generalized graph with the nodes with values A, B, C, D, and E, and I'm going to show how the values get passed upwards in the DP table. So we already know that for nodes like B, that value is going to be 0 because they have no outgoing edges. So when A asks B, it's going to get 0 plus 1 as a result. Now when A asks C, C is going to say, hold on, let me ask D. D is going to say 0 plus 1, and then C can say 0 plus 1 plus 1. Now E is more of a general case because we don't exactly know how much is here, but we can just assume that the dp of E would be x. So when A asks E, E is going to say x plus 1 because the distance between us is 1 edge. So let's fill out the dp for each of these nodes. dp of B is going to be 0. dp of D is going to be 0. dp of Z is going to be 1 plus the dp of D. I've already said we can assume that dp of E is going to be x. Now when it's time for A is going to check all of its children, and then it's going to pick. So that's how dp of A is going to be populated. Now, if there's a node that wants to know about A, it can actually ask about A, and A will return dp of A, and then whatever node is asking can reuse that value in its computation. So I've written the code, and I've split it into two parts. The first part is going to be the control logic, where we initialize the visited set in the dp array, and the second part is our recursive DFS function. So what we're going to do is take our adjacency graph, and our DAG is just going to be a simple ADJ, which is adjacency list representation of our graph. And we are going to go through each node, so 1 to n, because we don't know which node is actually going to have the longest path through it. Luckily, we have a visited set, which lets us skip it if we've already visited it. The reason we can do this is because if we've visited a node, then we know that we've updated the dp value of that node in our dp array. So to begin, we're going to call our DFS function. What we're first going to do is see if we visited that node. If we have visited it, we're going to just automatically return. It's a void type method, so we can just say return. Otherwise, we're going to set it to visited. Then what we're going to do is check each of its neighbors and see, hey, are you guys visited? So NEI stands for neighbor, and if it hasn't been visited, we are going to recursively call our DFS on the neighbor. So why do we do this? We're going to recursively check if we can get down to our base case. In other words, we want to visit the nodes which have no outgoing edges, and we're going to set them to visited so they can be reused in our computation. So once we've done that, once we've done our if check, all we have to do is see dp of I is going to be math.max of dp of I, what was already there, and we're going to do dp of neighbor plus 1. So all we're going to do is just check the neighbors, and then this DFS stack is going to return. Once we've gone through all the nodes and checked if they've been visited or we ran a DFS on them, we can take our dp array and see which value is the longest, and that's going to be the longest path in our entire DAG. Now let's talk about the time and space complexity. Alright guys, let's go over the time and space complexity. We know the space complexity is going to be O of big N because we've initialized a dp array and a visited array of size n plus 1. Let's talk about the time complexity. The time complexity is also going to be O of 1, and let's see how that happens. So in the beginning, we know we have a code that says from 1 to n inclusive. So let's start from 1. So 1 hasn't been visited, so we're going to recursively call. 1 is going to talk to both of its children, so 3 and 4. And then 1 is going to return. Now it's going to be 2, right? 2 is going to say, all right, come visit. And then it's going to try talking to its children, 3 and 4. But 3 and 4 are already part of the visited set, so it's not going to recursively call them. Then we get to 3, and we see that 3 is already visited, so we don't recursively call it. Similarly with 4, we see that 4 is already visited, so we don't recursively call it. Now all that is left is 5. So we visit 5, and 5 is going to check its children, but it's going to see that each of its children is already visited, so it's simply going to update DP of 5 using the DP values of its children. And since we visited every single node just once, 1, 2, 3, 4, 5, with 5 nodes, the time complexity is going to be O of n. Alright guys, if you enjoyed the video, please like, comment, and subscribe, and share it with your friends. And don't forget to hit the bell icon so you can stay updated on all the latest videos. Thanks for watching.